Today's video is going to focus on acid-base theories. So far we've talked about stoichiometry and stoichiometry in solutions and how that all works together. You've done a little bit of an introduction to acids and bases. You've talked a little bit about what a strong base versus a weak base is, and a strong acid versus a weak acid as well, and then some examples of each. Today I'm going to talk to you a little bit about the different theories and the progression of the idea of an acid and base throughout history. The first thing to understand is the properties of strong and weak acids, and similarly strong and weak bases. The pH of a strong acid is much below 7, 7 being neutral on the scale. The pH scale runs from 14 down to 0, 7 being neutral, 0 being very acidic, 14 being very basic. Both acids and bases, as you saw before in your previous note in the introduction to acids and bases, are very caustic, very corrosive, very dangerous, but also have but for very different reasons, and there are some other different properties that we'll review in class. But you can see again, looking at the strong acid versus strong base, you're looking at a very high ionization in a strong acid versus a very weak ionization in a weak acid. Sort of low, just less than 50% ionization. The rate of reaction is very fast in a strong acid, and it's very slow in weak acids. So weak acids, much closer to neutral. They don't totally dissociate, which we'll talk about what that means a little bit shortly. And it's a much slower reaction. So the first concept we're going to talk about is the Arrehenius concept of acids and bases. And it's originally was derived to explain how ions allow for electrical conductivity in aqueous solutions. And what Arrehenius came up with was the fact that acids were hydrogen-containing compounds. And often we symbolize that with HA, where H is the hydrogen and A is that back base. So an example would be HCl, hydrochloric acid, that we've talked about. So what acids do is they ionize and increase the hydrogen ion concentration in the solution, where a base, on the other hand, dissociates in water and increases the hydroxide ion concentration. So here, acids you're talking about H+, bases you're talking about OH-. Okay, so something like NaOH would be an example of a base. Okay, so this was a bit of a limited definition. Big one here is that H+ ions don't really exist in solution. What you actually tend to see is water takes on an H+ and becomes what we call a hydronium ion. So it's an H3O plus ion. Okay, so this is much more realistic and much more often what you would see. So looking at this, so for example, water you will see often, even in solution in itself, will split up into hydronium ions and OH-. A strong acid, on the other hand, as you can see, is almost completely dissociated into its H3O+ and then the other ion, okay, the anion. Whereas a weak acid, a lot of it all stays together. Right? You can see the HA mostly staying together, very little of the hydronium and the anion along with it. And the pH you can see a little bit higher. With strong acid, much lower. You get higher here with a weak acid. Strong base, similarly, you get almost total dissociation into the two ions, where in a weak base you're left with a lot of the base and a lot less of the two ions. And again, pH is a little bit lower. Right, so the more basic something is, that strong base, the higher the pH. Okay. So because of these problems, Bronsted-Lowry kind of started investigating these things separately, and they noticed that not all acids and base reactions involve water. Okay, and that was where the H and the H+ and the OH- came from. And so an acid actually becomes a proton donor to a water molecule. So no matter what it happens to be, the acid will donate a proton while a base accepts a proton from the resulting hydronium ion. And I'll show you an example of that in a second. but each substance is defined as a Bronsted-Lowry acid or base only for a specific reaction. Okay, so this is important, as a substance that donates a proton in one reaction could accept a proton in another reaction. And these substances are called amphiprotic, which means that amphi means that they can do both, and protic means protons. So they can both accept and give protons. If they're giving a proton, they're an acid. If they're accepting a proton, they're a base. So a little bit different than the Arrehenius definition, where we were talking if it had an H+, it was an acid. If it had an OH-, it was a base. Okay? So a conjugate acid is the product formed as a result of a base accepting a proton. Conjugate base, the product formed as a result of an acid donating a proton. And then the conjugate acid-base pair is the pair together. So you can see here, the acid, the H+, donates, here the acetic acid donates an H+ to H2O, so it's the acid. The base will, or H2O will accept that H+, so it becomes the base. And then the conjugate acid becomes H3O+, because it's accepted that, and the conjugate base is what gave up the H+. Okay? Now, Lewis is the final concept here. And this is a much more general acid-base model. It deals more with electrons than just hydrogen plus. A Lewis acid is an electron pair acceptor, where a Lewis base is an electron pair donor. Okay, so we're talking more about electron pairs being moved rather than H pluses being moved. Basically, a Lewis acid has an empty orbital that can accept a lone pair of electrons from another molecule, a Lewis base. This model is useful in explaining reactions that do not involve Bronsted-Lowry. So you would see that in the reaction of bromine trifluoride with ammonia. So ammonia, NH3, plus boron trifluoride looks like this. So you have your ammonium bonding to the boron trifluoride to create NH3BF3. What happens at the molecular level here is, as we remember from our Lewis diagrams, ammonia looks like this, and boron only having 3 valence electrons has this empty space up top. And you can see ammonia has this very nice base pair which it donates and bonds to the boron, creating this molecule. Much larger molecule, but everybody's much happier. There are no lone pairs available, and there are no empty shells available as well. Okay, so this is, you see this much less. Most reactions, most acid-base reactions are covered by the Bronsted-Lowry and even our Arrhenius concept. And we're going to focus mostly on Arrhenius here, but I want you to be aware of the different models. Okay?